In this video, we're going to do example 4, and we're going to integrate this using U substitution. So remember, your goal with U sub is to choose a U such that its derivative is being multiplied in the integrand. So sometimes it's kind of nice to write this all in terms of multiplication, right? Tangent squared theta divided by cosine squared theta, that's cosine of theta, all squared. The reciprocal of cosine is secant, so that's secant squared of theta. All right, and when you're doing this, maybe I even look at tangent squared as tangent times tangent, and secant squared as secant times secant. And it would be reasonable to consider choosing U to be secant theta. Why? Because du d theta, the derivative of U with respect to theta, is secant times tangent. So we would have a secant times a tangent for my du. I'll just write that. And I've got a U being secant theta. But what the heck would tangent theta be? Remember, when you're making a substitution for it to be effective, I have to substitute completely. I can't integrate theta stuff and U stuff. It's got to be all U. So what we're going to want to do here is I'm going to let U be tangent of theta. The derivative of U with respect to theta, the derivative of tangent, is secant squared. Yay! I have a secant squared being multiplied in the integrand. Du is secant squared theta d theta. All right? So U is tangent. So what's tangent squared? That's U squared. Maybe I even write this. Tangent squared is tangent times itself. So we've got U squared times a du, right? Now, if I choose to leave these limits as theta limits, I'm going to go ahead and have to back substitute. But I think I'd like to just substitute completely. Let's get, when theta is 0, what the heck is U? And when theta is pi over 4, what the heck is U? All right, so when theta equals 0, U, which is the tangent of theta, that's going to be the tangent of 0, which is 0. Happens to also be 0. If you know the graph of tangent, that's great. I like getting my tangent on the unit circle real fast. Tangent is y over x, and here I am at 0 radians. The slope of that line, that horizontal line, is 0. That's how I like to get my tangents pretty quickly. When tangent is pi over 4, that's on the line y equals x. The slope of that line is 1. Tangent of pi over 4 is 1. However you like to do it. So when theta is pi over 4, what is U? U is tangent of theta. It's tangent of pi over 4, which is 1. U is 1. And so we're going to go ahead and make these substitutions completely. We're now integrating as u goes from yellow to orange. U goes from 0 to 1. Of green squared of u squared times pink times du. And that is delightful. I'm going to just rewrite it without color. The integral of u squared with respect to u, we're just going to do power rule in reverse, adding 1 to that exponent, dividing by that new exponent. Fundamental theorem of calculus part 2 says that we can find this complicated area by evaluating this antiderivative function at these endpoints, going from 0, and these are u limits. U is 0, u is 1. All right? And what I was saying before is if you chose to not change those, if you left these limits being 0 and pi over 4, the common mistake would be to go ahead, to be excited, I got that antiderivative, and plug in the pi over 4 minus plug in the 0. But those are x limit, or sorry, not x, we're using theta. Those are theta limits, right? So if I left that, I would need to go ahead and substitute what the heck is u? U is tangent theta, do that back substitution, and then I could plug in these theta limits. But since we went ahead and substituted completely, these really are u limits, u going from 0 to 1. You don't have to write u equals, but I'm doing it just to emphasize that those are u limits. Order matters in subtraction. I'm going to plug 1 in first, minus plug in 0 next. So we've got 1 cubed all over 3 minus 0 cubed all over 3. So we've got a third minus 0, which is equal to a third, and we are done. All right. What have we figured out here? I'm going to pull up another graphic. Right. So here are some nice pictures from previous semester. So we were originally asked to integrate tangent squared over secant squared as theta went from 0 to pi over 4. In other words, we were asked to find the signed area under this curve, tangent squared over secant squared, as theta goes from 0 to pi over 4. When we made the substitution, what did we end up integrating? We ended up integrating u squared as u goes from 0 to 1. We were finding the area under the parabola u squared as u goes from 0 to 1, which I have drawn right here. And this area is the same as this area, right? Which is pretty cool. When we substitute completely, we're really deforming this area into another one that's easier for us to find. And the most profound part is Fundamental Theorem of Calculus Part 2 that says we don't have to find this complicated area from the definition. We don't have to take a limit of sums of areas of rectangles as the number of rectangles goes to infinity. We can instead ask ourselves a different question. What's an antiderivative for this function? Boom, right here, u cubed over 3. Let's evaluate that antiderivative at the endpoints. That length, a third, is the same as this area, which is the same as this area. Very, very cool. Classic mathematician. Answer a different question with the same answer. I hope this video was helpful.